Okay, just to get you thinking, what will keep you warmest on a cold winter's night? 1 kilogram of iron at 100 degrees Celsius or 1 kilogram of water at 100 degrees Celsius? Are they both the same? Will the iron keep you the warmest or will the water keep you the warmest? If you've never thought about this before, then this is a good kind of way of introducing you to the topic. If you know the answer, it's actually water. Water can contain a huge amount of energy for each degree Celsius you raise its temperature by, for the amount of water you have. Okay, so that's what this topic is all about. Welcome to the presentation on specific heat capacity. Take a moment to read the learning objectives and we'll continue. Okay, let's first look at the difference between heat and temperature. If you want a cup of tea fast, which kettle do you switch on? The half full one or the full one? Okay, it's pretty obvious that the half full kettle B, will heat up the fastest. It doesn't need as much heat energy to raise its temperature because it's got less mass in there. Heat energy is a measure of the internal energy in a substance and it's measured in joules. Both kettles will eventually reach the same temperature. With high temperatures, things feel hot and their molecules have higher kinetic energies. Okay, let's have a more specific definition of temperature and heat. If temperature is measured in Kelvin degrees, then the number is directly proportional to the kinetic energy of the molecules. Okay, so basically temperature is proportional, if it's measured in Kelvin, to kinetic energy of the molecules. Heat is a measure of the total energy in a substance, and it's a sum of both the kinetic energies of the molecules and the potential energies of the molecules. Okay, so potential energies, you can imagine them acting like little springs. Their static charges may be repelling each other, or they're forced together, and there's potential energy there in the elastic kind of springiness of the charge forces, and in the bonds of the atoms as well as the movement energy, the kinetic energy. So if you want to pause the video, maybe take a note of these two definitions, and then we can move on. Right, so let's have a look at how we go about measuring the specific heat capacity of something like water. Take, for example, 2 kilograms of water and try raising the temperature by 10 degrees from 21 degrees Celsius to 31 degrees Celsius and measure how much heat energy this takes with a joule meter. Okay, so here I have a joule meter, a power pack, a heating element and a thermometer. So the power pack supplies voltage and current. This thing tells me how many joules are going to go in. Right, so I switch it on. I get the temperature rise, and it tells me it took 84 kilojoules to do that. So I've switched it off now. It's taken 84 kilojoules to raise the temperature by 10 degrees Celsius. Okay, so I can say it takes 84 kilojoules to raise the temperature of 2 kilograms of water by 10 degrees Celsius. That's not such a useful statement. Let's see if I can try and make it a bit more generic. See where I got the numbers from, 2 kilograms and the 10 degrees Celsius. Okay, let's see if I can make it more generic. 84 kilograms divided by 2 kilograms means that I've actually taken 42 kilojoules per kilogram per 10 degrees Celsius. That's a bit more useful. Let's see if I can make it even more useful. 42 kilojoules per kilogram divided by 10 degrees Celsius gives me 4,200 joules per kilogram per degree Celsius. This is a much more useful number now because I can multiply it by how many kilograms I've got to find out how much energy it takes to raise the temperature of something by 1 degree Celsius, and so on. So let's start again, and this time I can define the formula for specific heat capacity. Specific heat capacity of a substance is equal to the energy required to raise its temperature by however many degrees, to change its temperature by however many degrees, multiplied by its mass. So if I just stick the numbers in that I had for this question, or this example, 84,000 divided by 10 degrees Celsius times 2 kilograms gives me 4,200 joules per kilogram per degree Celsius. Okay, so this is the formula we wanted to get. I can improve the accuracy of the specific heat capacity measurement. This time I'm looking at 1 kilogram of steel. And what I've got is actually, this is a cross section I've cut in half, just so you can see what's going on. A block of steel, and it's got 2 holes bored in it. One is for a heating element, and one is for a thermometer. Okay, and it's the same setup as before. We've got the heating element, power pack, joule meter, and I've got a stopwatch here as well. And why have I got a stopwatch? You don't only have to use a joule meter. Sometimes a joule meter won't be available, and you'll only be able to know the power rating of your power pack, so how many watts it's going to give, or you've just got a power meter. Okay, if you have that, then you'll have to use this formula. Energy is equal to power times time. Power is given in watts, which is actually joules per second. So for every second that goes by, you use, say if it's a 60-watt heater, every second that passes is 60 joules. So if you time how long it takes, you multiply time by power, you get the number of total joules that were put into this block. Okay, so we switch it on and we heat it, let's say for 5 minutes with this 30-watt heater. We get a temperature rise. The temperature rise was 14 degrees Celsius. But as you can see, these red arrows represent heat energy lost due to conduction, due to radiation, due to any form of heat loss, okay, or heat transfer. So this isn't going to be the most accurate change in temperature reading. Okay, so let's try and make it more accurate. This time I'm going to insulate my block with some foam to try and reduce any of these heat losses. Also, having this completely inside with not much hanging out the top, it's going to make it more accurate as well. The heating element. Okay, so this time I switch it on, heat it for 5 minutes, and this time you can see the temperature change. Everything was the same, but the temperature change this time is greater. This is going to give me a more accurate specific heat capacity measurement. Okay, use my formula. This time energy, I'm going to have to use the power times the time. Okay, so I've just substituted energy in with power times time there. Okay, the power was 30 watts. The time was 5 minutes, well, 60 seconds every minute, 5 times 60, and the change of temperature was 20 degrees Celsius, and it was 1 kilogram of steel. So I calculate that the specific heat capacity for steel is 450 joules per kilogram per degree Celsius. Notice that this is many times smaller than for water. Water is quite unusual. It has an incredibly high specific heat capacity. This comes in very handy for many processes that involve cooling or heating or lots of different areas. Okay, so let's have a look at this IGCSE exam question, worth 7 marks, which is a huge portion of the exam. Pause the video and carefully read the question. Have a go at it yourself. Okay, reasonably simple question, but easy to make mistakes on. There are 4 readings that you're asked to take. Here, 4 readings. What are they? Okay, you need to know the initial temperature and the final temperature. Those are the 2 things you would have to measure. You need to measure the mass and the time this took, because it tells you the power. You're going to have to know the time it took to know the amount of energy that went into it. Write down an equation in words or symbols that could be used to work out the specific heat capacity from the readings in A. So you've got to take these readings and make a formula from it. Okay, so specific heat capacity is equal to power times time divided by mass times the change in temperature, which is Tf minus Ti. You could put delta T here, but it's better to explain in more detail exactly what the calculation you're going to do. Explain why the value obtained with this apparatus is higher than the actual value. Okay. Because it's not well insulated, the temperature rise is less, so you need more energy for a temperature change. Okay. Heat escapes to the surroundings by conducting convection and radiation. Okay. State one addition to the apparatus that would help to improve the accuracy obtained. Okay. You could insulate the block by wrapping it in foam to reduce heat loss. Okay, thanks for watching. Hopefully you should now be able to state the difference between heat and temperature and be able to calculate the amount of energy needed to raise a given amount of a substance by a certain temperature. So some key points from this video. Basically, different materials require different amounts of energy to raise their temperature, and for this reason it's important that for engineers or doing any kind of work with temperature or heat, we need to know their specific heat capacity, exactly how much energy it takes to raise their temperature for a given mass by a certain amount of temperature. Okay, any comments or suggestions, welcome. Thank you very much for watching.